Hello, welcome back. This is Jason Harrington, and today we're going to talk about exact equations. Now, the time for this is a little bit longer because some of you haven't had Calc 3 yet. So I want to give you sort of a visual understanding of level curves before I start to dive into what an exact equation is. Then I'll give you some more concepts behind it, the definition. Number 4 is actually pretty important because that tells you exactly how to identify exactness. So you can check to see if something is or is not exact. And then I'm going to do a few examples, and then I'm going to talk about what happens if you need an integrating factor to turn something that's not exact into something that's exact. So let's just talk about plotting multivariate functions. If I want to do a surface plot, so everywhere I put in an x and a y, I have a height. So I'll have my height z at the point x comma y. And you can see that's going to create some hills, valleys, maybe saddle points. But you'll notice that if I put a ball or a marble here on this surface, it'll probably roll down. And if I put a marble here, it'll probably roll inside and just stay at the bottom there. Now what we can do is we can look at what's called a level set. And I called this a surface through a surface because I actually have two plots here. This blue line here is just, or this blue plane, that's just z is equal to 0.5. And we can see that when this function passes through this plane, you have a little part there. So everything on this curve touches that, meaning that the function is going to be equal to 0.5. So this blue part, f of x comma y, is equal to 0.5 here, right? And if I move this slice up and down, then I can get different points. And the idea is that we can look at something, instead of looking at a 3D object, which is sometimes hard to visualize, we can just look at a flat surface. So here's what basically a color level curve looks like. Now what we see here is that when the colors are darker, that means it's going down negative. So here we have 0 is going to be basically sea level, for example. And then if you go negative, that means you're going below sea level. And if you go positive, you're going above sea level. So just by looking at this particular level plot, we see that here's where this mountaintop would be, right? And then here's where we see that the hole in the ground would be. Now, of course, at this point, you may be asking, well, what does all this have to do with difference equations? Well, let's remove all the fluff and all the colors, and we basically just get level curves, right? So, for example, here, we said this was the level curve for when f of x comma y was equal to 0.5. Now, the question is, what if that is a solution to a differential equation? What if that curve is a solution? And of course, you don't have to have just circles or weird blobs. I mean, they can be a magnitude of different shapes. So the question here is, what if this is a solution? What if this level, this specific curve, is a solution to an ODE? The question is, how would we find f? So that's the main goal, is how to find that multivariate function, f of x, y, and then of course our initial value condition will set what our c value would be. So before I start doing all this, let me introduce some quick notation here. You remember from Calc 1, or single variable calculus, if you have y is equal to f of x, then we can write the derivative dy over dx is equal to f prime of x, which is, and then I can split this up, dy is equal to f prime of x dx, which is just another way of saying that the delta y is just an approximation of the derivative at some point times delta x, if we're doing a linear approximation, for example. But for multivariate calculus, we have very similar notation and very similar meaning. So if I have a function z is equal to f of x comma y, so it's a function of x and y, then the total differential, or sometimes called the total derivative, is going to be the partial of f with respect to x times dx. And notice these two things don't cancel. And we have the partial of f with respect to y times dy. And let me mention a little bit as to where this comes from. But here is why all this is very important. Because this is what the whole section basically boils down to, is how does one calculate the slope of the tangent to a level curve, f of x comma y equals c? Well, it's actually pretty easy, knowing a little bit of 3 tools or multivariate calculus. What I do is I have a multivariate function that's in terms of f, x, and y is equal to some constant. I take the derivative with respect to x on both sides. Now, of course, the derivative of a constant is just 0. And don't forget, this one I'm going to have basically the concept of a multivariate chain rule, because the inside function has y and x inside of it. Remember, y is a function as well. So that's going to turn into the partial of f with respect to x plus the partial of f with respect to y times dy over dx. And if I multiply everything through by dx, then guess what? I get the total differential just equal to 0. So the equation for the slope of f of x of a level curve, f of xy is equal to, actually it doesn't have to be 0, it can actually be, I should make a little note before we print this up, but that can be any constant. Can be just expressed as the total differential equals 0, and then solving that. Excuse me. So now let's sort of work backwards here, and hopefully you can see the pattern as to how these things actually work. So suppose I have a surface, and I want to set this equal to a constant, so I have f of xy is equal to x squared y squared plus x is equal to some constant, c. Doesn't really matter what we call it. If I take the total differential or the total derivative, I get df is going to be the partial of f with respect to x times dx plus the partial of f with respect to y dy. And of course the derivative of a constant is just 0. Now we just have to figure out what these pieces are. So here I'm going to start with f, the multivariate function, and I'm going to take the partial derivative of that with respect to x. Now when I say partial derivative, because some of you may not have had multivariate calculus, that just simply means that I'm going to take x as the variable, and everything else is just treated like a constant. So in this case, here I want to take the derivative of f, and taking the derivative, partial derivative with respect to x, so everything else is held sort of as a constant, and the only thing I'm taking the derivative of is just x. So in the first case, I have, that's going to turn into, let's see, 2x y squared plus 1 dx plus the partial derivative of f with respect to y. That's just going to turn into 2x squared y. And don't forget, the derivative of x with respect to y is just 0, right? This is just a constant. And so that's what I'm left with here. dy is equal to 0. So this is now an ODE form that we have. We have 2x y squared plus 1 dx plus 2x squared y dy is equal to 0. So now the remainder of this lecture, what I'm going to do is I'm going to start with this, and I'm going to work backwards. And here's what you do. The idea is I'm going to integrate this with respect to x, and then I'm going to integrate this with respect to y. and see if I can get it to fit an equation. All right. So now let's go ahead and try to work backwards in this case. So now I'm going to start with this. I have 2x y squared plus 1 dx plus 2x squared y dy is equal to 0. Now, just for simplicity and for the rest of the lecture, I'm going to call this first term here a function m of x and y. I'm going to call this second term here a function of n of x and y. So, let's try this out. So step 1, I'm going to integrate m of x and y, and I'm going to integrate it with respect to x. And now I'm going to have the integral of 2x y squared plus 1 with respect to x. And just like with the partial derivatives, if it's not an x, I just treat it like a number or a constant. Okay, so the first term I've turned into x squared times y squared plus, and then the antiderivative of 1 is x. Now, this is where you got to be careful, particularly for those that are new to the concepts of having to work with two functions. Normally, in Calc 1, I would just say plus c and be done with it, but that actually doesn't work in this case. So that's the part you got to be careful about. Remember, I'm integrating with respect to x, so I want to find something whose derivative is going to be 0, right? And you'll notice there's a lot of options. I can actually put plus 1, because the derivative of 1 is 0, that's going to work. But notice I can also put y. And why would I put y? Well, that's a good question. Well, I would put y down because what's the derivative of y with respect to x? It's 0. And really, anything in there with y's and numbers is going to be have derivative 0. So instead of a constant number, right, I'm going to say plus any function of g, or sorry, any function of y. So g is a function of y. Any function of y, the derivative is going to be 0, going backwards. Now the second term I'm going to do, I integrate n of xy, and I do the same thing, dy. So that's going to turn into the integral of 2x squared y, okay, dy. And that's just going to turn into x squared y squared. And just like before, because I'm integrating with respect to y, any function of x has the derivative of 0. So that's going to work out. So I have h of x. And remember, you can check yourself before you wreck yourself, as some people say. If I take the derivative of the first term, I get this. I mean, again, with respect to y. And if I take the derivative of h of x with respect to y, I get 0. So this actually works. Now, here's what you need. You need something that will satisfy both of these little guys' conditions here. All right. So, let's write it out. So I have now that f of x, y, the first thing I'm going to need is they both have x squared, y squared. So that's easy enough. I can definitely take care of that. And the first line tells us that I need a plus x. But is that going to work, right? And the answer is yes, because remember, I can set this to anything. I can set to anything and it will work. I just need to find one that will satisfy both of these boxes. So in this case, if I let h of x equal to x, it now satisfies both, and then the g of y I can just set equal to 0. And that's now a function that satisfies both conditions. Now this first example is a very simple one where really I'm just missing an x in this one. This one I'm just missing an x, and I can just put it into this function. But sometimes it gets a little bit more complicated than that. And so this is my actual function that I have. And then, what's the answer to the ODE? Well, the answer to the ODE, remember, is a level set or a level curve. So it's just going to be x squared, y squared, plus x is equal to a constant, right? And that turns it back into a level curve that I showed you all those pictures of. And this is the idea for how to actually solve it. It gets a little bit more complicated, so I'll do a lot more examples with this. So basically those level curves and then integrating and finding ways to manipulate them is exactly what we need. But what exactly is an exact equation? So this is your definition. I forgot to put a little colon here. But exact, the differential form, I'm going to have a function of x and y times dx plus a function of x and y times dy is said to be exact in the rectangular form if there is a function such that the partial of f with respect to x is equal to m, and the same function, if I take the partial derivative of f with respect to y, I get n. And that is that the total differential of f satisfies this condition. And if it's equal to 0, then we call that an exact equation. So just by itself, we just say exact, but if it's equal to 0, it's an exact equation. Now, here's what would really suck. If you ask yourself, how do you know if this is going to be solvable or if there even is an answer? Well, the nice thing is that this theorem is going to save you quite a bit, because when you start to look at random ODEs, you can just check them real quick. If I take the derivative of this with respect to y, and I take the derivative of this with respect to x, and if they're the same, then that means it's exact. And it's as simple as that. So it's a very simple test to see, hey, is this going to work like an exact equation or not? And if it doesn't, then you have some more options that you can do, some more techniques to solve them out. Okay, so now let's go ahead and start with a better problem here. So for this example, I want to solve this. So I have 2xy minus secant squared x dx plus x squared plus 2y dy is equal to 0. So I'm going to call this first term here my m, and I'm going to call this little term here my n. Now the first thing I want to do is I'll always want to test for exactness, even if it doesn't ask me to, because I need to make sure that the method works. So let's test. And the way I test is, the first thing I do is I take the partial of m with respect to y. And so if I take the derivative with respect to y up here, that means the x's are all held as constants, so that's just going to turn into 2x. So I have 2x here. And now I'm going to take the partial derivative of n with respect to x. And by the way, the derivative of secant squared of x with respect to y, there are no y's here, so that's just 0. Now if I go over here to this side, and I want to take the derivative with respect to x, the derivative of x squared is 2x right? And then the derivative of 2y, there's no x's there, so that's just going to be 0. And luckily, these two things are the same. So that means it is exact. Now the next thing I have is I'm going to integrate m with respect to x. So 2, I'm going to integrate m with respect to x, and that's going to turn into just the integral of 2xy minus secant squared x, the whole thing with respect to x. And just like before, I'm going to hold the y as a constant, so the antiderivative of 2xy is just x squared y. All right? And then the antiderivative of secant squared is just tangent x. So that's minus tangent x. And again, this is the part where you want to be cautious about, because remember, we're taking the antiderivative with respect to x. So it's no longer just a constant, but remember, it's an entire function. And because I integrate it with respect to x, that means that any function in terms of y will also work. Because remember, the derivative of anything in terms of y is just 0, right? I mean, that's why we use the constant in Calc 1, because the derivative of a constant is 0. But now in multivariate calculus, or when you have more variables, then you can simply say, well, I'm holding the y as a constant when I integrate with respect to x. And so now that's my new quote-unquote constant term. All right, so now I'm going to integrate n with respect to y. So that's going to turn into x squared, the integral of x squared plus 2y dy. And so if I integrate the first term with respect to y, remember the x squared is now a constant, so that's just going to turn into x squared y. All right. And now the second term, if I integrate the second term with respect to y, I now just get y squared. So that's going to be plus y squared. And just like before, but now instead of being a function of y, like the previous case, because I integrate it with respect to y, now I can have any function with respect to x. Now I need to find one single function that satisfies both of these. It has to satisfy both of these equations. It has to be able to fit into both of these. So the third thing I have is that my function f of x, y, well, we already have the x squared. They both have this term there, so I know that my function is going to have x squared, y squared. All right. Now, if I look at this first term here, I have tangent of x. Now remember, this little guy here can be any function of x that I want. So what I'm going to do is I'm going to make this equal to negative tangent of x. So now they both have tangent of x. Now, I need the tangent of x because it's in the first line there. Because this tells me that I have to have negative tangent of x. And then with this one says, hey, I have this function, I can make it whatever I want. So I'm also going to make it negative tangent of x, so now that these two guys will match up. So now I'm going to have minus tangent of x. All right. Now, only thing I have left is that plus y squared, which I need because of the second line. So this line here tells me I need a y squared in my answer. But the question is, can I make the first one have a y squared and still be okay? And the answer is yes, because here, this g of y's, we can make this whatever we want, as long as it's in terms of y. And so this little guy here, I'll make that equal to y squared. And now they both match beautifully, and everything works out nice. So that turns into plus y squared. So this tells me now that my answer, is going to be x squared, y squared, minus tangent of x plus y squared is equal to some constant c. Remember, it's a level set. Remember, our solution is going to be that level set that we have. And so that's our final answer for that problem. All right, so for now, this example here, we have solved this ODE. We have 1 plus e to the x times y plus x times e to the x with respect to x. Hold on a minute, that doesn't look. X times e to the x plus 2 dy. That's interesting. So again, I just checked for exactness in my head real quick, and that's actually not exact. Seems like I'm missing something. Let me fix this. I'll fix it on the lecture notes before I post them. It should be a little y somewhere. Some little y right here. Cool. How could I forget that little guy? So, I have, let me rewrite this out. Now it's interesting, like I said, if you were to check this without that little red y in there, you would actually see it's not exact. Which tells you can't use this method. But luckily I fixed it real quick. X e to the x plus 2. It's really terrible to work on an ODE for a long time, only to realize, hey, you can't even solve it. So for this little guy, I'm going to call this m. And I'm going to call this little guy n. So the first thing to do to check this is I need to first take the derivative. I'm going to go ahead and just check to see if I can even work it. Hopefully this does. So I have, if I take the derivative with respect to y, the derivative of the first term, the derivative of 1 with respect to y, that's just 0. In the second case, the e to the x is just a constant, and so a constant times y is just that constant. So I have e to the x plus, and then I have the same thing that happens on the other term. And so what we see is that the derivative of x e to the x times y is just x times e to the x, because the only thing that we have that has a y in it is just a y. So a constant times y is just whatever that constant was. So that's what we have when we take the derivative with respect to y. Now let's check the second guy. The second guy, this, I'm going to have to use the product rule. So I'm going to have the first times the derivative of the second, which is just e to the x, plus the second times the derivative of the first, which is 1. And those two are in fact the same. So what that tells us is that the derivative of m with respect to y, is the same as the derivative of n with respect to x. So it is exact. And we can finally solve it, which is pretty cool, right? I found that y. All right, so now let's just go ahead and integrate both sides respectively, or both terms respectively. So for 2, I want to integrate m with respect to x. And that looks a little hard for right now, but let me go ahead and try it anyway. I'm going to write this as 1 plus, well, 1 plus x e to the x, I'll factor those out, times y. And I want to take the derivative with respect, or take the antiderivative with respect to x. Now this one, a little bit of finagling, you can get that that's going to be x plus xy e to the x. I did that one. That one's pretty nice. And just like I've been making this in red the whole time, because I integrate with respect to x, then now I'm going to have a function of y. So again, that's my cautionary tale. Everyone wants to put just plus c, and then they get the answers wrong, and they don't know what's going on. But remember, always check yourself. the derivative of g of y is just 0. And if I take the derivative of this piece, I should get that. Now, as a little trade secret, I did do this integration. I just didn't have enough space to put it on my page. But it's basically, I would expand it out actually. That might make it a little bit easier to integrate. Now, if I integrate in with respect to y, here's what I have. I'm going to have the integral of x e to the x plus 2, and I'm integrating with respect to y. And so I'm left with x e to the x times y plus 2y. And again, in this case, I have plus, instead of a constant, it's going to be a function of x because of how I was differentiating, or integrating, I should mean. Now, if you look at this, we want a function, one function that satisfies both of these conditions, both of these exactly. So 3, I have f of x comma y, and let's just see if we have any pieces that kind of stand out. We do notice that they both have this term in it. Okay, so we know that f's got to have that in there. So f's got to have x, y, e to the x. Now the next question is, can we have this x, or do we have to do something a little different? And the answer is no, because remember, this h of x, I can pick whatever I want. Instead of being a number, it's a function. So I'll just let this be equal to x. And now this function, or sorry, this term here and this term there match. So I can now successfully put x back into my f. And likewise, I have a function of just y that I can pick whatever I want. And I have 2y in the second equation. So that's what I'm just going to let g be. This is going to be equal to 2y. And so now my answer for this is going to be xy e to the x plus 2y. That is my equation. And my level set is going to look like this. xy e to the x plus 2y is equal to a constant. Now in this case, we can actually solve for y pretty easily. So let's actually go ahead and do that. Solve for y. He's a nice little guy. Put him by himself here. So if I have xy e to the x plus 2y is equal to c minus x, I can factor out a y on the left-hand side now, and I'll have x e to the x plus 2 is equal to c minus x. So that means that my answer, my final answer after all the smoke clears, is going to be y is equal to c minus x divided by x e to the x plus 2. And that's it. Cool. Okay, whoa. I got a little scared when I saw this. All right, so let us take a look at this example, which seems scary on the onset. Hopefully it won't be too bad. So for this first thing, I'm just going to set this equal to m. And for this, I'm going to set equal to n. And let's check to see if this thing even works. Let's see. My hope is to say, nope, it doesn't work, and then go on to a nicer, easier problem. But something tells me that's probably not going to happen. So m sub y, if I take the derivative of m with respect to y, then in the first case, I get, or the first term, I'm going to have, I'm taking the derivative with respect to y, so I'm going to have 1 over x times e to the y. So I have 1 over x times e to the y over x. And then if I take the derivative of this term here, I got to use the product rule. Okay. So that's going to be, the product rule is, I'm going to have the first y over x times the derivative of the second, which is 1 over x e to the y over x, plus the second, which is e to the y over x times the derivative of the first, that's just 1 over x. Okay, now, if we look at this, what we see is that these two terms cancel. And this just leaves us with this middle term here, which is going to be equal to negative y over x squared e to the y over x. And now I check the n sub x. So now I'm going to take the derivative of just this term with respect to x. And remember, it's easier to think of this little guy as just saying e to the y times x to the negative 1. So that should make it a little bit easier to think about. So I'm going to take the partial of this term here. So I have, let's see here, that's just going to be e to the y over x, and then on the derivative of x to the negative 1, that's just going to be negative x to the negative 2, so that's going to turn into y over x squared. And these two pieces, unfortunately, are the same, so we do have it as exact. So this is exact. I mean, I should say that excitedly. This is exact. So now let's actually see if we can process this. Cool. Okay, so now let me show you a neat little trick so that you don't really have to worry about these, computing all these things, particularly trying to find the antiderivative of this huge piece here, because that's truly daunting. So let me write this out. If I were to try to integrate m with respect to x, I'm just going to say, okay, that's hard. Let's not worry about that right now. Let's see if I can find a way around it without having to actually compute this giant integral. But I do know how to integrate n with respect to y, because that one is in fact pretty easy. So if I integrate, because that's just that one little term, e to the y over x dy, I'm going to get 1 over x, which is just x, e to the y over x, and because I'm integrating with respect to y, I now have a function in terms of, say, g of x. So this whole thing should simplify down to just being x e to the y divided by x plus g of x. Okay. Now this is the part that should make my life a little bit easier. Remember, I know that the function f has to have this term, and it has to have some parts with the derivative, or sorry, the parts of g of x. And if I take the derivative of this with respect to x, I should get this function back. So instead of integrating and comparing the two results, what I'm going to do is I just found the second result, and now I'm going to differentiate it and compare it to that without having to integrate. Because, well, it's hard and I don't really like to integrate big, massive, crazy things. So let's do this. So now 3, we know that f of x comma y is going to be now x e to the y divided by x plus g of x. And I also know that if I were to take the derivative of f, the partial of f with respect to x, I should get m. So let's try it out. So the partial of f with respect to x, again, this is going to be a product rule and then g prime. So I end up having, this is equal to e to the y over x minus y over x e to the y over x plus the derivative of g is just g prime of x. And now our m, we have e to the y over x minus y over x e to the y over x plus 1 over 1 plus x squared. So that's just rewriting this big M right here. Now you'll notice, now this is the cool part. We didn't actually have to figure out how to integrate this big beast on this left-hand side here, because basically just knowing this term pretty much gave it to us. So if these two things have to be exactly the same, well, these are already the same, these are already the same. That means the derivative must be 1 over 1 plus x squared. So that tells us that g prime of x is equal to 1 over 1 plus x squared. So then g of x is just equal to the arctangent of x plus a constant. All right, but again, we can pick that particular constant to be 0. Right? We can pick this to be whatever we want. I'll put this off in red. You know, we're just going to let that be equal to 0 just to make the function easier. So for my actual function, well, we already wrote the function in 3, but now we actually know what g is. So f of x comma y is just going to be equal to x e to the y over x plus the arctangent of x. And so that means our answer is a level set of that curve. So we have x e to the y over x plus the arctangent of x is equal to a constant. Now you can be as creative as you want. So there's a lot of people out there that are like, you know, really clever at saying derivatives and antiderivatives. Remember, you're constantly going back and forth between the two. So if you encounter something hard, sometimes it's actually easier to just skip it and then see if you can rearrange the pieces like I did here. Cool. Now, just like last lecture, I said sometimes things don't really work out the way you want them, but what you can do is have what's called an integrating factor. Multiply everything through by an integrating factor and just fix it. So in this case, suppose we have a function of x and y times dx and a function of x and y times dy, but it's not exact. So it doesn't actually work out. If you test it, it won't be exact. So here's the thing that we can do. We can sometimes just multiply through by an integrating factor. And I sort of gave away the big surprise, but you want the integrating factor, and you'll see why, to be in terms of either x or u. Or sorry, x or y. Okay, let's try it out. Now the question is, how do you find this mu? So here's what I'm going to do. Write this down. I'm going to have mu times m dx plus mu times n dy is equal to 0, because I just multiply each term through by mu. And remember that condition that we need for exactness. Here's what we need. So one, we need, now remember how we test it to see if something's exact? We need that test to pass. So I have this first term here, and I need for that, if I take the partial derivative with respect to y of this guy, mu times m, that is going to be equal to, let's see, the first times the derivative of the second, let me just put m sub y, plus the second times the derivative of the first, mu sub y. And I also need this second piece. If I take the derivative with respect to x, these two things should match up. So that means I'm going to have the partial derivative with respect to x of mu times n. And again, I'm going to use the old product rule here. So I have the first times the derivative of the second plus the second times the derivative of the first. And what this tells us is these two things have to be the same in order for all this to work. So let's do that. So 2, I'm going to set up this equation. I'm going to have mu times m sub y plus m times mu of y, mu sub y, is equal to mu times n sub x plus n times mu sub x. And what I'm going to do is I'm going to put all of my mu's to one side. Okay. So I'll put all the mu's on the right-hand side and everything else on the left-hand side. So on the left-hand side, I have m times mu sub y minus n times mu sub x is equal to mu, and I can go ahead and factor this out, n sub x minus m sub y. All right, now, solving this, and by the way, this is multiplication here, that function mu. This, quite frankly, this is hard. I'm not going to lie, not going to sugarcoat it. It's horrible. But let's make some conditions here. I'll make 2 cases. What I'm going to do is I'm going to suppose we have 2 cases to consider. And you may ask where this comes from. Now remember, we can construct this mu function however we want. We just need to find one mu that works. So we can make choices about this mu, right? We just want to pick one. So let's easier. So if mu depends only on x, for example, so i.e. it's just mu of x, or if mu depends only on y, i.e. mu sub y. Then check this out. If mu only depended on x, well, check this out. The derivative of mu with respect to x, that still stays, but the derivative of mu with respect to y, well, that just goes away to 0. And then it becomes easy to solve, right? Likewise, if mu only depends on y, then the derivative of mu with respect to x, this whole thing goes to 0. So let's go ahead and start this out. So here's what I have. I'm going to start with this. I have, let me just rewrite that equation I have. So m times mu sub y minus n times mu sub x is equal to n sub x minus m sub y times mu. I put the mu on the right-hand side. So let's just take a look at the different cases. Case 1, suppose mu only depends on x. Only depends on x, i.e. it's mu of x. So what that means is that mu sub y is just identically equal to 0. So now I'm left with n times mu sub x is equal to n sub x minus m sub y times mu. And if I were to solve for just the mu sub x, I would get mu sub x is equal to n sub x minus m sub y divided by negative n times mu, which is actually the same thing as just saying m sub y minus n sub x divided by n times mu. And this is separable. Okay, so that's separable. So basically what I have is the derivative of mu with respect to x is equal to this function that I have here. I have m sub y minus n sub x divided by n times mu. And you can simplify that, and you'll see that you end up getting mu of x is equal to e to the integral of m sub y minus n sub x divided by n dx. Okay, so that's my first integrating factor that we have, if that one works out. And 2, if I were to say, suppose mu only depends on y, i.e. mu of y. So what that says is that the derivative of mu with respect to x, that's just 0. Okay? So that tells us that this term is now 0. And here's what we're left with. We're left with m times mu sub y is equal to n sub x minus m sub y times mu. And again, this is going to be separable. So we have mu sub y is equal to n sub x minus m sub y divided by m times mu. And just like before, that's separable. And that's easy to solve. And so what you end up having is mu of y is just going to be e to the integral of n sub x minus m sub y over m. And then I want to take the antiderivative of that with respect to y. And here's what we have. So we have these two integrating factors depending on which one you think would work best. So I'll do some examples and we can make these choices. Now these two aren't really that difficult to memorize because if you think about it, the y, you're going to have, remember when you check to see if something is exact, you take the partial derivative with respect to y to see what happens. So you start with m, and then over here on the top you have my, and then of course you have the other term n of x minus in the front. And likewise here, I mean actually I forget all these rules because, I mean not the rules, but I always forget all these little sayings because students always email me new things all the time. Sometimes students will actually have a poem that rhymes and makes these things fit. You know, e to the integral of, well, I can't really make that rhyme, but there's all kinds of mnemonic devices out there. In my head, when I have mu of x, my x term, right, I know that I'm going to have this n, and then the last term is also n of x, leaving me with my as the only thing left over, and I know it's always subtraction. So if I have the bottom is m, then I have my and nx. Anyway, I'm sure you can Google mnemonic devices and find one a whole lot easier than the way I think. So now the question is, well, which one do you use? Which one do you use if you have two choices? Right, I'm sure that's what you're thinking. So here's what you can check. Basically, if m, take the derivative of m with respect to y minus n sub x divided by n is a function of x alone, then you're going to use mu of x is equal to e to the integral of m sub y minus n sub x over n let's see, that's just going to be dx. And then That's the first one. The second one, if, check this out, n sub x minus m sub y over m is a function of y alone, then you use the integrating factor is equal to e to the n sub x minus m sub y divided by m dy. All right. And let's go ahead and do some problems, and we can see if we can make these choices. All right, so let's now go ahead and work this one out. Now, again, I'm just going to call these things, this first little term here, I'm going to call him m, and I'm going to call this little guy n. Just see sort of what happens there. I'm always going to check for exactness. You just got to see what happens. Again, if you just meet any ordinary difference equation off the street, which happens to me on a daily basis, you don't know if it's exact or not, so you got to be very careful. So I'm going to check. So I'm going to take the partial derivative of m with respect to y, and then I just get 1. And then I'm going to take the partial derivative of n with respect to x, and that's going to give me 2xy minus 1. And after some heavy calculations, you can see that they're different. So it's not exact. I'm just kidding about the calculations. It's pretty obvious. So m sub y does not equal to n sub x. So now I have to try and figure out an integrating factor and see if that works. So 2. Let's find an integrating factor if possible. And I'll show you what happens if it's not possible. Okay, so the first thing I'm going to do is I'm going to try n sub x minus m sub y divided by m. And I'm going to see if I can get that into a function of a single variable. Now luckily when you did this check up here, we've already taken the derivative. So again, that's another reason why I like to check, because then you've pretty much done most of these derivatives already. So n of x is just going to be 2xy minus 1. And then I'm going to then subtract 1 divided by m, which we have as 2x squared plus y. And in the top, I can simplify that. I can factor out a 2 and write that as xy minus 1 divided by, and in the bottom I just have 2x squared plus y. Okay, so this doesn't work. See, this depends on x and y. So don't use this. So this one doesn't work for in our case. So let's try the other one. So if I try m sub y minus n sub x divided by n, then the m sub y I have 1 minus, and the n sub x I have 2xy minus 1, all divided by n, which is x squared y minus x. Now right off the bat you're like, maybe that's not going to work. But we got to simplify it first, right? So if I simplify this, then that's going to turn into 2 minus 2xy divided by x squared y minus x. So in the top I can go ahead and factor out a 2, 1 minus xy, and in the bottom I can factor out an x, which just turns into xy minus 1. Aha! These two things cancel, leaving me negative 1. So this whole thing just simplifies down to negative 2 over x. And yes, this little guy works. Now if it didn't work, then you can't use an integrating factor, which is sometimes possible. You have to use a different technique if that doesn't work. So now my integrating factor, we know, is mu of x is equal to e to the integral of negative 2 over x dx which just works out to be equal to e to the negative 2 natural log of the absolute value of x, but I can write that as e to the natural log of, without the absolute values, just x to the negative 2, because remember when you square something it makes it all positive. And so my integrating factor is actually just x to the negative 2. So now I just need to multiply every term through by this. So that is now my integrating factor. That's my integrating factor. So I'm going to multiply every term by x to the negative 2 and see if I can make that exact. Okay. So once I do that, so whoops, I don't want to use red just yet. I only have so many colors to play with. So our ODE becomes, if I multiply it by x to the negative 2, I'm going to get just 2 plus y times x to the negative 2 dx, plus the first term just becomes y minus x to the negative 1 dy equals 0. So that's our new ODE. Just multiplying through by something doesn't change the answer, but so let's go ahead and work this little guy out. All right, so from our new ODE, we have, I'll just rewrite it again, we have 2 plus yx to the negative 2 dx plus y minus x to the negative 1 dy equals 0. Now it still has that new ODE smell, so let's go ahead and just name them our normal things. I'm going to overload m. I'm just going to call this one m again, and I'm going to call this little guy n. And the first thing I'm going to do again, I'm just going to check. Did this thing even work, right? Is it exact yet? Hopefully. So if I take the partial derivative of m with respect to y, that's going to give me just x to the negative 2. And if I take the derivative of, n with respect to x, I get x to the negative 2. And yes, oh, that feels so good. Yes, this is now exact. So this is exact now. Okay. So now our second step for solving the new ODE becomes, I'm going to integrate m with respect to x. And so that's just going to turn into the integral of 2 plus yx to the negative 2 dx. And if I integrate 2, that just becomes 2x minus, and if I'm integrating x to the negative 1, or sorry, negative 2, I gave the answer away, that's going to be minus y x to the negative 1. And that's a function of g, or sorry, not a function of g, but g of y. It's a function of y. And now if I integrate n with respect to y, I get the integral of y minus x to the negative 1 dy. Okay, so on the left-hand side, or sorry, on the right-hand side, I should have 1/2 y squared. And if I integrate x to the negative 1 with respect to y, I simply have y x to the negative 1. And now I have a function of just x. And now I need to figure out what my new function f is. So I have f of x comma y. And we do know that, oh, that's neat. So we basically both have, we know that our function f has to have negative y times x to the negative first in there. And let's see. If I have 1/2 y squared, then I can simply just let this constant function, I mean, it's not really a constant function, it's constant in the sense that the y's or treat it like constants. But that's just going to be 1/2 y squared, so that that term will fit. And then likewise, I can put this, I can put 2x inside there. And now I have a function that satisfies both of these conditions. And so now I will have 1/2 y squared minus yx to the -1 plus 2x. So last but not least, my answer is going to be 1/2 y squared minus yx to the -1 plus 2x equals c, to turn it back into a level function, right? Or a level curve that we had from f. And that is our actual answer that we have. Whew. That felt good. I'm glad that one worked out nice. All right. So that's basically the gist. And don't forget that try, if you want to try one until you get the integrating factor that actually works. And if you can't find one, then you can't use an integrating factor. You've got to move on to something else. All right. Well, good luck with your homework and everything else. And I'll see you next time.